All right. So for Unit 7, the topic is on chemical kinetics. So the notes has been shared also in Google Classroom. I think this morning I've already shared, so you can refer to the notes. And from chapter 6 onward, since your module is on general chemistry for pharmacy, but actually from chapter 6, 6, 7, 8, and 9, the topic of chemistry is more towards physical chemistry, okay? So in chemistry, there are three main branches of chemistry. You have organic, inorganic, and physical chemistry. For organic chemistry, you will start to learn next semester, but uh, starting from thermodynamic, chemical kinetics, equilibrium, that is mostly physical, and it involves doing some calculation as well, which is mathematics. So even though it is chemistry. So on Unit 7, as the name goes, the title, Chemical Kinetics, what will be covered in this chapter is uh, you will learn what is reaction rates. Okay, basically how does a reaction rate is being measured, and this has to be done experimentally. Okay, it cannot be done theoretically on paper. So experimental data must be obtained for you to have a reaction rate or to calculate a reaction rate. And then we have rate loss and integrated rate loss. These two are related together. It's just that in integrated rate loss, the time and also the concentration of reactant and products are being taken into account, and some of them involve or we are trying to transform them into straight line graph, okay, which is it fulfill the y equal to mx plus b graph. And then you will learn what is half-life in terms of the reaction. So basically, what is the time taken for the concentration of reactant to go to half, okay? And then the Arrhenius equation, how rate constant changes with temperature. And lastly is on the catalyst, the substance that is added in the reaction that change the rate of the reaction but does not being consumed in the reaction itself. So let's take a look at the introduction first. So the chemical kinetics is basically the study of how fast a chemical reaction occurred. So we want to measure, let's say you have a reaction of acid and base titration, basically how fast the acid can neutralize a base, for example. And that data can only be extract experimentally. Okay, you cannot simply assume or deduce on paper. So the goal is to understand chemical reaction at the molecular level and speed of reaction is measured by the change in concentration with time. So what kind of concentration? Either we can see from the perspective of a product or from the perspective of a reactant itself. So throughout the reaction, a reactant concentration will decrease over time, but for a product, it will start from zero, and at the end of the reaction, the concentration will eventually increase. So some of the important factors that affect rates of reaction, you have the reactant concentration, and then temperature of the reaction that you are doing, whether this reaction requires heat or whether it requires very low temperature. So these depend on the reaction being exothermic or endothermic itself. and then the action of a catalyst, whether there is a catalyst involved, if you add catalyst to the reaction or not, and then pressure of gases, reactants, or products. So if the reaction involves gases, so high pressure probably will increase the rate of reaction. Later we will see how all of these factors affect the reaction rate. And lastly is the surface area. Okay, the surface area we are talking right now is in terms of the reactant itself. So why does it cause the difference in terms of rate of reaction? So the besides information about the speed at which reaction occur, so the kinetics also will tell you on the reaction mechanism of that particular reaction that you are doing. Okay, exactly how the reaction occurs, whether it involves intermediate or the reaction proceeds directly from reactant, it immediately produce the product. An example is you look at the three jar over there. The first one, you have all those red dots. Okay, that is actually, we consider that to be A. So after 20 minutes, the blue dots, which is B, we can say that is the product start to form. And after another 20 seconds, okay, the concentration of B increases, okay, while A decreases. So we can say that A is the reactant and B is the product. So rate of reaction can be determined by monitoring the concentration of the reactants or products, okay, as a function of time. So we are visualizing the concentration based on time taken for the reactions, okay. So concentration is written as the bracket, the square bracket. Okay, it will normally be written something like this, and whatever is your reactant will be written inside. Let's say you have carbon dioxide, for example, so it will be written like this. So if you notice that reactant is written in a square bracket like this, so it denotes this is the concentration of that particular reactant or products, okay. So the rate of reaction or reaction rate for the reaction A to B, so A reactant, B is the product, there are actually two ways, okay, two ways to view or to measure the rate. One is, like I said earlier, how fast we see the reactant disappear or how fast the products appear. Okay, there are two ways in which you can view, from the angle of product or from the reactants. So reactions are reversible. So as products accumulate, that is formed from the reactant just now, they can begin to turn back to the reactants, okay, for a reversible reaction. So early on, the rate will depend on only the amounts of reactant presence. But as soon as they are mixed together, let's say there are more than one reactants or two or maybe three reactants to be mixed together to form the product. Once they are mixed together, then you should start measuring the time, okay, in order to monitor the concentration. So the the most useful way of measuring the rate of the reactions in terms of change in concentration per unit time is by using this formula, which is rate is equal to delta concentration of the reactants over delta T, which is concentration, the changes of concentration for the reactant over the time taken from the end of the reaction and the initial time, okay. And the most common unit used will be molar per second. So this is the concentration, and then unit of time per second, whereas the concentration molarity has the value of moles per liter. So in thermodynamics, we actually trying to determine whether a reaction takes place or not, but in kinetics, that particular reaction, we want to check how fast does it proceed. So another way of writing the rate, which is this one, okay, has been simplified as this. For example, this reaction of A, the reactant, forming B, which is the product, okay. So the rate is written as delta A, which is the concentration of A at certain time, let's say 1 minute, minus the concentration of A at time 0 over delta T, which is the time taken. Let's say it's 1 minute, so it should be 60 seconds. So if you notice that the rate of A, okay, there is a negative sign. So this is to let you know that the concentration of A is actually decreasing with time. So that's why it is negative. While B, the symbol is positive because over time, the concentration of B is increasing because it starts from 0. So at the end of the reaction, the concentration will definitely be more than 0, right? So we are going to see the rate after this later. But before that, we want to introduce a new term, which is the rate constant. So over here, on this rate law over here, it does not taken into account a constant. This constant basically is different for every types of reaction. So what is this rate constant? First, we look at the factors affecting reaction rate constant as in the earlier slide. The first one is basically temperature. So if you supply more heat at higher temperature, reactant molecules will have more energy to collide with each other. So this is basically based on collision theory, in which that the reactants have to collide with each other to produce the product intended. And if based on kinetic theory, increasing temperature will increase energy, thus the molecules will have more energy so that it can move faster. And then in terms of concentration of reactant, as the concentration of reactant increases, so does the likelihood that the reactant molecules will collide. That means the amount of molecules that is available to collide with each other increases versus if let's say you have a very small concentration. That means the amount of reactants is less. And then in terms of catalyst, so these actually speed up reaction by lowering activation energy, which we will see later how it does the lowering of activation energy. And number 4 is the surface area of a solid reactant, which is if you have more area for the reactants, okay, the more chances it has to be in contact with each other. Okay, and last, pressure of gases, reactants, or products. So this is only applicable if you have gas as your reactant or your product, as a, if you increase the pressure of that particular reaction, the molecules of the gases tend to be close to each other, thus it will have higher chances of collision. Okay, let's take a look at this example. Okay, concentration, how does concentration affect the reaction rate constant, which is the K just now. So we have this nitrogen pentoxide, N2O5, okay, dinitrogen pentoxide. It forms nitrogen dioxide and also oxygen. So if you look at the reaction equilibrium, for every 1 mole of oxygen that is appears, okay, 4 times as many moles of NO2 will also appear. So 1 mole over here, and then 4 moles of nitrogen oxide. In the meantime, twice as many moles of N2O5 will be disappearing as each of the molecule of oxygen gas form. So basically, the changes in concentration of both reactants and product is inversely proportional. Okay, inversely proportional to their stoichiometric proportion. That means the way it is written in terms of uh, rate rate law will be rate is equal to -1/2. Okay, you have here the number of moles that is required. Okay, it is not proportional. If it is proportional, it will straight be 2 over here. Okay, it will be written 2, but it is inversely proportional. So it will be written as 1/2 delta concentration of N2O5, okay, over delta T. So we have here negative because this is the reactant. So reactant over time, the concentration will definitely decrease. So hence we have negative sign. While for the product, positive for nitrogen dioxide and also positive for oxygen. So oxygen, there is no numbers appearing in front because there's the value is actually 1, while for NO2, the number is written as 1/4. Okay, 1/4. That is how the rate of reaction will be written.
Sir,
Yes?
nak tanya boleh?
Yeah, sure.
Um, kan reaction rate. Lepas tu kenapa kena ada reaction rate constant?
Nanti dekat bawah, we will see why you have a rate constant. Okay?
Okay.
Okay. So now taking into account reaction rates and stoichiometry. So basically this reaction, okay, the general way to write the rate is like this, in which you have rate equal to 1/A, which is the number of moles, concentration, delta concentration of A over delta T, or you can also write it as negative 1/B, okay, the number of moles for B, delta concentration of B over dt, or from the perspective of the product itself. But always make sure for the reactant you have negative value in front, while for product it is positive. Okay. So here basically as the earlier representation, here only the first pictures time 0. So this is time 0, only reactants, while after a certain period of time, at the end of the reaction, the products is more than the reactant itself. So back to the question from your friend just now, why there must be a constant. So this is following what we call here rate law. So in general, rate of reaction increase as concentration increases, since there are more collision occurring between reactants. So the overall concentration dependence of reaction rate is given in a rate law or rate expression. Okay, so this is why we have to introduce the rate constant just now. Okay, a general rate law of reaction will look like something like this, equal to rate will be equal to K, which is the rate constant, and then we have the concentration of A, okay, concentration of A, and as well as concentration of B, being that there are more than one reactants. And this concentration have what we call as the power of M or power of N. So M and N exponents are called as reaction orders. So basically, from what we have seen, all of this, okay, rate, and then the introduction of rate constant, all will lead to this rate loss, meaning that the acceptable uh, way, okay, that is being used right now to calculate the rate of reactions. So this is like, if you imagine like in mathematics, the derivation from start until you get the end of the formula that is being used. So that is how rate constants comes into play, because the rate's constant value will be different for every reactions. Okay, example, uh, let's take a look at this reaction of ammonium ion NH4 plus NO2 minus. Both are in aqueous solution. It produces nitrogen gas and also 2 moles of water. So the following observation from several experiments were made. So these data are obtained experimentally. So you cannot just assume or propose it theoretically. Let's say you doubles the concentration of the ammonium ion, it will also doubles the rate of the reactions, meaning the value of this rate. Okay, as you doubles, let's say A, the rate of reaction will also doubles. And here we have through the data from experiment, if you doubles the NO2 minus concentration, which is this one, okay, the rate will also be doubles this value, even though the ammonium ion remain constant. So you just increase this concentration, you double it, but the ammonium ion is constant, the rate will still be double. Thus, the rate of the reaction will be expressed as rate equal to K, and then you have this concentration of ammonium in bracket, and then concentration of NO2. So this reaction, if you remember, the M and N earlier is said to be the reaction orders. So what is this reaction orders? So the reaction is said to be, in this case, okay, we look at the example first. The reaction is said to be first orders with respect to ammonium, which is this one, okay, and first order with respect to NO2. So how come they reach the conclusion that the NH4 is first order and NO2 is also first order, all based on this experimental data, in which that uh, you have this order of reactions, okay, another term. So a reaction is said to be zero order if the concentration change does not affect the rate of the reactions, meaning that let's say you double, you triple, or you quadruple the concentration of the reactants, the final product will still be the same. The rate of reaction is also the same. So we can say that it is a zero order. But the first order, if doubling the concentration causes the rate to double, while a second order, the rate of reaction will quadruple, and so on. If you have third order, then 2 to the power of 3. That means the rate of reaction will be 8 times. So that's how, for this particular reactions, so the conclusion was made that the order of the NH4 plus is 1, and also for NO2 is 1, based on the data provided from the experiment. But the overall order, okay, from this rate law, the overall reaction order will be the sum of the reaction orders, meaning you have to add both M and N values, which is 1 and 1. So you have to add 1 and 1. So we will say that the whole reaction order will be second order, meaning that if you increase the concentration of both the reactants, then the rate of the reaction will be quadruple. So the rate constant K, this value, does not depend on the concentration. Okay, it doesn't change with concentration. Okay, but K will be different value for each reaction. Even if you change the concentration, you want to increase or if you want to decrease the concentration, the value of K, which is the constant, is basically the same. And the value of K can only be obtained from experimental data. How to obtain the value of K from experimental data? If you look at this rate law, okay, if you look at this rate law, concentration of A, concentration of B can be obtained through experimental data. As for example, you can try to double up the concentration of one reactant and see what is the reaction rate, meaning time taken for the reaction to finish maybe become half or whether it becomes slower. So you can actually uh, collect the data, and from there we can actually calculate the concentration the rate constant for each reaction. So how does the calculation is being done? Basically, this is what I said earlier, which is you may plot a graph from all of the data available through the experimental data that has been obtained. Let's say for a zero order reaction. For zero order reaction, we know that the concentration of the reactant does not affect the rate of the reaction. So that's why over here rate for zero order reaction will be equal to K. Okay, for zero order, the rate is equal to K. As what is said earlier over here, the concentration of reactant, change in concentration of reactant produces no effect to the rate of the reaction. So that's why rate is equal to K in terms of zero order reaction. But in terms of first order, so which is this one, okay, rate does not change with concentration, where you have here AT is equal to negative K plus A0. So AT is actually concentration of A at time after a certain time that is taken for the reaction to finish, while A0, which is this one, is the initial concentration of A. So from this reaction that you can actually plot, so the equation has a general form of a straight line in which you can use this y equal to mx plus b. So if you plot concentration of A at time t versus time taken, okay, a straight line with slope of negative k can be obtained, in which that the intercept will be concentration of A at time 0. So from this value of slope, so this is how the value of rate constant can be calculated. But all of the data of this concentration of A at time t has to be obtained through experimental. Okay, you cannot calculate based on theory only. Then to convert the rate law into a convenient equation so that to give concentration as a function of time, okay, the book has the derivation, which is the textbook that I'm using. Mostly I refer to this textbook written by Raymond Chang, okay, which is a very uh, uh, how to say, simple enough, but all of the content is suitable for general chemistry. Okay, you may try to search it online. I think there are a PDF version of it because in our library there is a hard copy, but you cannot go to the campus right now. Try to find the PDF version. Okay, uh, to obtain this, it involves certain derivation and integration. So for first order reaction, you only have to remember this formula over here. No need to know about the derivation. So ln or natural log concentration A at time t will be equal to negative kT plus ln concentration of A at time 0. So from this formula, we can also actually obtain a straight line graph in which the value of negative k here, the value of the slope will be the value of the negative k, is this one, okay? And then for second order, this formula is being used, okay, in which now the concentration of A is inversely proportional. So 1 over concentration of A at time t equal to kT plus 1 over concentration A of time 0. This also, if you plot, will give you a straight line in which the value of the slope is equal to the rate constant, which is k. Okay, but the uh, value of y and x will be different in terms of second order and first order. In terms of first order, you have to convert it all of the value of concentration into ln or natural log. Okay, and actually, let's say over here an example how to determine the reaction order if you are given a set of data. So the decomposition of nitrogen dioxide at 300 degrees Celsius is described by the equation of NO2, in which that it decomposes into nitrogen oxide plus half a mole of oxygen gas. So here we have this data in which that at time 0, the concentration of NO2, so this is with respect to the reactant, okay, NO2. So 0.01 and then time 50 seconds, so the concentration starts reducing. So from here, we can actually try to input this data into one of the formulas that is stated above. Let's say over here, we try to fit it into the first order uh, uh, formula of ln concentration of A at time t equal to negative kT plus ln A at time 0. But if you notice that the graph does not give you a straight line, so in this case, it is slightly, curve like this. So it's not a straight line. So we know that this actually does not fit. So it is not a first order reaction. If you try to do it in, let's say, a second order formula, which is this one, okay, and you are able to obtain a straight line like this, in which that the slope will be the rate constant, okay, which is the k value. So this is a straight line, sorry. Therefore, the process is said to be in second order for NO2. So this is how, if you are given a set of data from experiment values, you can actually try to deduce whether it is a first order reaction or second order reaction based on how it fit into the formula of the y equal to mx plus b. And then going into half-life. So half-life is actually the time taken for the concentration of a reactant to drop to half its original value. Meaning, let's say you start with 100, at what time it will take time taken for the concentration to reach 50. Let's say it's 20 seconds. And then once it reach 50, another 20 seconds, it will reach 25. So that is half-life. So for first order reaction, the half-life is calculated by this formula, which is T, the symbol of half-life is written as T1 over 2, okay, subscript. So half-life is written as 0.693 over K. So K is the rate constant. So once you know the rate constant from the graph that you obtain, you can actually calculate the half-life. But for second order, the half-life formula is 1 over K times the concentration of the reactant at time 0, while for zero order reaction, the half-life is equal to concentration of A initial over 2K. Okay, so let's take a look at an example for a first order reaction. So first order, the half-life calculation is this one, okay, 0.693 divided by the rate constant. So number of half-lives over here in the graph. So let's say for the first half-life, and then you have the second half-life. So the concentration basically half at each of these time interval. Another example over here. So let's say you have a few of these, maybe 20, okay, of the reactant at the start of the time. So after the first half-life, it will become 10. And then after another half-life, the reactant will become, the concentration will become half, then it will be 5, and then it will become 2.5. Okay, so until it become, until the reaction finish, then the concentration of the reactant also will reach approaching 0. Okay, so all of that, the rate loss and the integrated rate loss, I put into this simplified table, okay, for you all. Okay, don't worry, even though I cannot see your face right now, but from the experience of teaching your seniors, I know there's a lot of confused confused faces. Okay, but all of the earlier slide leads to these values, which is rate, first order, second order, and then this one you need to see lah, okay, general second order. Okay, in which that you have to know the rate loss, okay, integrated rate loss, and also half-life in order for the reaction. Okay, for first order, the rate loss will be written as rate equal to negative Ka, while for second order, if there is more than one reactant, it will be written as negative K with the concentration of A and B. If there is only one reactant, then it will just be A. And then the integrated rate loss can be used to calculate the value of K. If you have all of the data from the experiment, you can try to plot a graph in order to obtain the value of K, because that is the only way how the rate constant values can be calculated. Okay, and the half-life of each of the order. Okay, for first order, the half-life is 0.693 over K, while for second order, it's 1 over K times the concentration of A times 0. Oh, I forgot to include the zero order. So maybe in your notes, you can add for zero order in terms of the half-life. All right. Okay.